All right, good morning, class. Can everybody hear me okay?
Yes, good morning.
All right, let's get started. Let's see, let's make some room for number one here. Put that on silent. There we go. All right. In the 2010 census, the population of San Antonio was 1.334 million people. See, 3 years later, in 2013, the population rose to an estimated 1.39 million. So let's look at A here. What was the exponential growth rate during this period? Well, let's see. Let's write down what we know here. So in 2010, the population, so I'll treat that as principal. 1.34 million, that's what it initially was. So I'll write that as a principal here. And then 3 years later, the amount is 1.39 million. So, and the time is 3 years. And so since populations grow continuously, we're using this formula. So we need to find the growth rate, R. Okay, so to solve for R, we can divide both sides by P. Now we can take the natural log of both sides because we want to get that R out of the exponential. So the natural log e to the RT, those undo one another. And so now to get R, we just divide both sides by T. R is 1 over T, natural log of A over P. That's our formula that we want right there. Now we just plug in our numbers. T is 3. Let's see, 1390000 1334000. And let's see what the calculator says. 1390 divided by 1334. Dang it, hit the wrong button. All right, now natural log. I divide by 3, and I get approximately 0.0137, which would be 1.37%. All right, any questions about that one?
I did a different equation. I did the V E with the power of K times T.
Yeah, so something like this, V equals V naught E to the KT.
Yes, I did that one.
Yeah, that's fine. It's the same formula if you look at them. You just use different letters. So yeah, that's just fine. So ultimately you should have got the same answer though, right?
Yeah, I got the same answer.
Yeah. So you just chose different letters to represent your quantities, and that's just fine. So let's look at B. Use the growth rate found in part A to estimate the population in 2030. So here we need to solve for A. We need A equals PE to the RT. So we use the same initial population. We're using this growth rate. But in this case, the time, since it's 2030, that would be 20 years. And let's see what we get. Times 20. E to that. Now multiply by 1,334,000. We got 1,754,752, something like that. But really, since they're only giving us accuracies up to a few decimals, we should really round this off to like 1.75 million. Because we know it's not going to be accurate up to the person because the numbers they gave us were rounded off to, you know, one or two decimal places in the millions. So I'd say 1.75 million. Let's see. C. Estimate when San Antonio will hit 2 million people. So we're using the same formula here, but we want to solve for time. So technically, all of this right here is exactly the same. It's just this last step. From here, we're solving for t instead of r. So we would have t equals 1 over r, natural log of a over p. So we have 0.0137. And so here the amount is going to be 2 million. And then my principal. Let's see what this calculator tells us. 2 million. 0.334 million. We take the natural log, divide by 0.0137, and approximately 29.6 years. So if we add 29 years to 2010, this would be in the year 2039. Or 2040 if you're rounding up. So. All right, any questions? Let's look at number 2 then. So Jeff owes $838 to a debt collector. So that's our amount. And he borrowed money at 7.25%. Interest is compounded continuously. So we use this formula. And he failed to make payments for 2 years. So how much did he originally borrow? So we need to solve for P. So we could divide both sides by e to the RT, which we can rewrite that as a negative exponent if we wanted to. Either way is fine. All right, so our amount here is 838.13 negative 0.0725 times 2. So let me see. Negative 0.0725 equals times 2 e to the x times 838.13, and I get $725. All right, any questions? All right, let's get a quiz then. Quiz number 22? Is that right? That one was, yeah, 22. Let's see. That's the one we just did. So we can do this one here. Page is this? This is page 195. Page 195. Pick out another one here. Do number 12 here. This one's from page 196. So let's see, it's 10:41, so 15 minutes. It'll be 51, 10:56. We will get back together. 10:56. All right, class, welcome back. Let's see if we could figure out how to do these problems. So number one, if the number of telephone solicitations increases exponentially, continuously, how long will it take to double your number of annoying phone calls if the growth rate is 12% per day? All right, so we have a rate of 0.12. Excuse me. So we're doubling the number of annoying phone calls. So that means our amount is twice the principal. Okay. So let's see, how long will it take? So we need to find the time. So we have amount equals PE to the RT. All right, and we've done this several times already, but we'll solve it again. To solve for the time, divide by the principal. We take the natural log of both sides. Those undo one another. So we have RT equals the natural log of A over P. So if we're solving for the time, we divide both sides by the rate. And that's what we have. So now we just need to plug in our numbers. The rate is 0.12. Now our amount is twice the principal. So we replace A with 2P. So notice the P's here cancel out. It doesn't matter what the initial number of phone calls was. So the P just falls right out of the equation. We have natural log of 2. So it's the opposite of the half time. It's the double time. So we take 2 and or the half life. It's the double life here. Take 2, take natural log. Now divide by 0.12. We have 5.78. In this case, it would be years. No, it's 12% per day. So this would be days. All right. Any questions about that one? All right, let's look at number 2. So certain radioactive decay can be modeled by the function R equals e to the kt, where R is the ratio of remaining material K is the rate of decay, T is the time in years. So when 1,000 years have passed, so it says T is 1,000, and they say R is 0.65. So after 1,000 years, the material still has 65% of its radioactive energy. Find the rate of decay. What sign is it and why? So we need to find K here. So we start off with R equals e to the KT. So if we're solving for K here, we can take the natural log, both sides. Those undo one another. We have KT was the natural log of R. So if we went K by itself, we're dividing by T. So they're saying when T is 1,000, R is 0.65. So let's see here, 0.65, take the natural log, I'll divide by 1,000, you get a negative 0.00043. All right, so percentage wise, this would be negative 0.043%. All right, so the rate of decay here is really small, and it's negative. So why is it negative? Because it's decaying. Negative or decay. All right, any questions? All right, so yeah, that's a really small percent, but 1,000 years have passed. So 65% of the radioactive energy is still left. It's lost 35% of it. All right, so moving on. Okay, so on page 197, we want to be able to solve equations with different kinds of logs. So remember our inverses, logarithms and exponentials are inverses. So natural log, that's a log base e, is an inverse of e to the, right? So the same thing goes for these. If you have log base 7, the inverse of log base 7, the inverse of that would be 7 to the x. Okay, so log base 7 is the inverse of the exponential with 7 as the base. So if we want to get the x out of there, the opposite of log is exponential. So we do 7 to the power of both sides. All right, so those undo one another. We have x minus 2, 7 to the first power is 7. Add 2 to both sides, we have x equals 9. So number 2, since it's a log base 2, we need to do 2 to the power of both sides. So those undo one another. We have 2x plus 6. 2 to the first is 2. So subtracting 6. Now divide by 2. So these aren't hard. All you're doing is exponentials to undo the logs. Okay, so number 3 here, since it's a log base 6, we'll do 6 to the power of both sides. That goes away. We have x minus 2, 6 cubed. Use my calculator so I don't mess it up. 6 times 6 times 6 is 216. So adding 2 to both sides, we get 218. All right, this guy here. First, let's deal with this 2. Let's turn this into a problem that looks like that. So the first thing we want to do is divide both sides by 2. Now this is just like the previous problem. We'll do 7 to the power of both sides. All right, those undo one another. 7 to the 1/2 is the same as square root of 7, right? So if we add 2 to both sides, we have x is root 7 plus 2. All right, same thing here. Let's isolate the log. All right, we're gonna move that 2 over here. So 1 minus 2 is a -1. Now we'll do 2 to the power of both sides. If those undo one another, we have 2x plus 6. 2 to the -1 is 1/2. It's 1 over 2 to the first power, right? So if we subtract 6 from both sides, let's see, 6 would be 12/2. This is -11/2. So now divide both sides by 2. So 11/2 turns into 11/4. All right, number 6. Let's isolate the log again. So we'll add 2 to both sides. Now we'll do 6 to the power of both sides. Yeah, x minus 2, 6 squared is 36. So adding 2 to both sides, we'll get a 38. Let's look at these. All right, number 7, how do you solve y equals e to the x for x? So you start off by taking the natural log of both sides. All right, this one, when they say log here, they really mean log base 10. So if they don't write the base, it's implied that it's log base 10. So we do 10 to the power of both sides. That goes away and we're left with just x. So this one, since it's a log base 3, we do 3 to the power of both sides. Those go away, that x comes down. So here is something that's important. This is really useful. Right here, okay. It says that if you have a log, if you have x to a power, you can take this p, the exponent, and just bring it outside the log and multiply. Okay. So yeah, if there's an exponent inside the log, you can bring that exponent and put it outside the log and multiply. Those are equal. Okay. Let's see, let's look at an example, I guess. What if we did log base 10 of 10 squared? All right, this is going to be equal to 2. Log base 10 of 10 10 to the second power, okay? Versus 2 times log base 10 of 10. So if we just took the 2 and put it out front, all right, what would this be equal? Well, 10 is the same as 10 to the first power. So this right here is 10. I mean, it's 1 because our exponent is 1. So we have 2 times 1, which is still 2. Okay? So just an example to show that they are equal. So this is the power property of logarithms. So for these, this is the same thing as 3 times the natural log of x. We just bring the 3 out. This one, since the whole thing is to the 5th, we can say this is 5 times log of x minus 2. Now what you can't do, what if I had this? All right. Since the whole thing isn't to the power of 5, only the 2 is, this is not this. Okay. All right. The whole thing has to be to the 5th power. All right. Since the square root is a 1/2 power, this is 1/2 log base 5 of x. All right, this is the same thing. I'll rewrite it here. We have the 5th root of x squared. All right, the 5th root means to the 1/5 power. That's what that means right there. That means to the 1/5. So when you have a power to a power, you multiply them. 2 times 1/5 is 2/5. So now we could take this and bring it out. This is 2/5 natural log of x. Number 14. We have room for number 14 up here. All right, it's b to the c. We just bring the c out. C natural log of b. Okay. So we're going to solve, approximate to 3 decimal places. Okay, so we're solving for t. It's in the exponent here. Let's fix this a little bit here. 1 minus 0.07. 1 minus 0.07. All right, that right there is 0.93. This is to the t power, right? All right, so if we're still trying to get to the t, let's see, let's get this 500 over here. So we have 250 over 500 equals 0.93 to the t power. 250 over 500, that's just 1/2. All right, now, what do we do with this, right? If it was 3 to the t, we would just go log base 3, and that would undo it, right? Is there a log base 0.93? Is there such a thing as this? It really doesn't matter which log we use here because of that trick that we just saw, this power rule. We can use any log we want. Check it out. If I take natural log, I can take the t and put it out front. T natural log of 0.93. So if I divide both sides by this guy, I have t is natural log of 1/2 over natural log of 0.93. All right, so I could have done log base 10 or any log I want. All right, natural log, I picked it because it's only 2 letters. It's the quickest to write. So whenever you have some kind of ugly exponential with t up there, or whatever your variable in the exponent, you can use any log you want. Just do it to both sides, and then you can take the your variable in the exponent and move it right out. Boom. So it turns out this was the same thing. If I'd have done log base 10 instead, I'd have ended up with this. Those happen to be equal. Okay. So let's see. I can do natural log. I got a negative 0.693,147 on the top, and then 0.93, take a natural log, got a negative 0.7257. So let me divide these. 0.693,147 divided by 0.07257. So they're both negative, so those cancel out, and I get a 9.551. I wanted 3 decimal places. That's why I put so many decimal places here. All right. The goal would be able to punch this into your calculator without approximating till the very end, because I did an approximation here, and then when I divided, there's a third approximation, which you don't want to do, but I have a simple calculator here, and I can't type it all in the way I want to. Okay, so let's do number 16. Okay, so we have the t is up there in the exponent again. So I do first, let's figure out what this is. I have 0.07 divided by 12. All right. So this is 1 minus 0.00583 bar 12t. So let's divide the 500. All right, so we have 100 over 500. All right, so 100 over 500, that's 1/5. And now I'm gonna put these numbers together. 1 minus 0.00583. So this is 0.99416667 to the 12t. Okay, so at this point, I turn this basically into the same thing we had right here. A number equals a number to the variable we want. So here we can do natural log or log base 10. Whatever log you want. So that allows us to take this and put it out here. So I have this. It's equal to 12t natural log of this stuff. So t here is equal to this guy divided by, all right, we need to get rid of the 12, so we'll divide both sides by 12, and we divide both sides by this. There. So in our calculators, let's see, I'll do the top. 1 divided by 5, It's 0.2. Now natural log that, I got negative 1.6094379. Now down here I have 0.99416667. Take the natural log, multiply that by 12. I got a negative 0.070249. All right, and actually when I do this, I should be doing my approximately equal here on all of these because I am approximating. All right, so at this point, I'll type these in 1.6094379 divided by 0.070249. I get a 22.925. All right, any questions about these so far? It's going to be the same trick over and over again. All right, if you have a real calculator, it's a lot easier. You can do without approximating at all these steps, right? You can type it all in and just do one approximation at the end, which is the goal. All right, this one, if we divide both sides by 500, we'll add these two numbers together. This is 1.01 to the t power. Okay. So 1000 divided by 500 is just 2, right? So now, because the t's in the exponent, you can do log base 10. I prefer natural log. And that allows us to take the t out. So natural log of 2 was t times natural log of 1.01. So t is the natural log of 2 to the natural log of 1.01. Right, so 2 natural log 0.693147118 and 1.01 natural log 0.00995,033. 0.693147118 divided by 0.00995,033. This gives me 69.661. I know there's a way to store numbers in here. I've just never done that. So anyhow, that should be accurate to 3 decimal places. I think I have enough decimal places here for it to work out. Let's look at 18. Okay, well, this time we have a log base 2. We can just do 2 to the power of log base 2. And 2 to the power of -3. So we rose at each side as an exponential. So those will go away. The 4x minus 1. 2 to the -3, that would be 1 over 2 to the third, which would be a 1/8. So we add 1 to both sides. 1 is 8/8. So this gives us 9/8. So divide both sides by 4. 8 times 4 is 32. 9 divided by 32. 9 divided by 32. So 3 decimal places is 0.281. Number 19, we'll do 3 to the log base 3. That goes away. 2x plus 1, 3 to the 4th. 3 times 3 times 3 times 3 is 81. Subtract 1 from both sides. Divide by 2. We have x equals 40. Okay, let's get rid of this 5 first. We'll isolate our log. So dividing both sides by 5. All right, we have -10 over 5 is a -2. Now we can do 4 to the power of both sides. So we got a 5 minus, try that again. 5 minus 2x. 4 to the -2, that would be 1 over 4 squared, or 1 over 16. So we'll subtract 5 from both sides. To get a common denominator, multiply this by 16 over 16. So 5 times 16 is 80. So we got 1 minus 80 over 16, or -79/16. So that's what -2x is. So divide both sides by 2, and the minuses cancel. So we have 79 over 32. 79 divided by 32. To 3 decimal places, 2.469. If a to the u equals a to the v, then u equals v. So what they're saying is, because these are both 2 to the power of, we can look at this and just say x minus 4 is 3x plus 7. All right. And the reason why is you can always take log base 2 of both sides. All right, these undo one another, and you're left with just the exponentials. Now, looking at this, that doesn't mean if I had a 2 to the x plus 2 to the 7th equal 2 to the 3x plus 7. I could not look at that and say, this is not the same thing as, oh, x plus 7 equals 3x plus 7. That doesn't work. It's because the entire thing, it's 2 to the entire thing equals 2 to the entire thing. Exactly this form. Okay. So over here, though, what we can do something about this 27 here. 27 is 3 to the 3rd power. 3 times 3 is 9 times 3 is 27, right? And then that's to the x minus 1. So I replaced 27 with 3 to the 3rd because I had a 3 to the power over here. Now when I raise an exponent to an exponent, we multiply. So to the power of 3 and then to the power of x minus 1, that's the same thing as 3 times an x minus 1. So what that tells us is we can say 2x is 3 times x minus 1, or 3x minus 3. So let's see. If I subtract 2x from both sides, I got an x, and I add 3 to both sides. I got x equals 3. Oh, I never finished this one over here, did I? I just said, okay, that equals that. So let's see, if I subtract x, then subtract 7. So x is a negative 11 halves. So let's do some more of these. So this one we have 2 to the power of stuff. We can rewrite 32 as 2 to the power of something. Let's see, 2, 4, 8, 16, 32. 32 is 2 to the 5th. So we can just say 2x minus 1 is equal to 5. So 2x is 6, so x is equal to 3. Over here we can do the same thing. This is 5 to some power. See, we got, I'll use my calculator. 5 times 5 times 5 times 5. So that's about 4 times. 1, 2, 3, wait. 5 times 5 times 5 times 5. Yeah, so 4 power. So in this case, we have x is equal to 4. Let's finish these and then we'll take our break. Okay, so since we have 4 to the power of, let's see, 64 is that 4 to the power of something? Let's see, 4 times 4 times 4. Yeah, this is 4 cubed. So we could say 2x minus 1 is equal to 3. So 2x is 4, so x is 2. Over here, let's see, what I can do is 32 isn't the power of 8, but I can rewrite these both as powers of 2. 32 is, let's see, 2, what is it? 2, 4, 8, 16, 32. That's a 5 there. 32 is 2 to the 5th, and 8 is 2 cubed. So an exponent to an exponent. So at this point, we could say 5x is 3, or x is equal to 3/5. Okay, 16, that's 4 squared, right? And being 1 over, I could rewrite that as 4 to the negative 2. So I have x equals negative 2. Over here, I can do these, both these numbers are powers of 2. 8 is 2 cubed. And then 4 is 2 squared. All right, so this is 1 over 2 to the 2x, or 2 to the negative 2x. So I can say 3 equals negative 2x. So x is negative 3/2. Let's take a 15-minute break. We'll come back at 11:33, 48, at 11:48. Continue on. All right, class, welcome back. Let's move on here. There's some more homework. And more homework. All right, let's summarize these. All right, when the unknown is, explain how to solve examples we've seen. Okay. All right, when the unknown is the final amount equals PE to the RT. Explain how to solve. Well, you just plug your numbers in here. So let's see examples. The pH, half-life, and compound, continuous compounding of interest. Continuous compound. All right. Plug in your numbers. All right. The initial amount. All right. We use the same formula here. We'd have to divide both sides by e to the RT. All right. Which can be rewritten as e to the negative RT. All right. These you can have the same ones, pH, half-life. So how you solve it, that's how you solve it. All right, exponent of base E. Yeah, you take natural log of both sides of the equation. Okay. Yeah, same example. All right, exponent of base 10, you take log base 10 both sides. Okay, you typically won't see that. You will see it, let's see. No, you don't see it in many of those. You can see it in half-life. I forgot what the formula for the pH was though. Might have to look the formula for pH again. Forgot what page it's on. I'll probably end up looking for it forever. All right, exponent of base B. Take log base B, both sides. So yeah, you see that in compound interest because you have amount equals P 1 plus R over N to the NT. In this case, they're calling this B. Right, the argument of natural log. All right, you do E to the natural log of X. E to the other side of the equation. You see that in compound interest a lot. Continuous is compound interest. Argument of common log. This is the same as log base 10. All right, we do 10 to the log base 10. Gives you your X back. Argument of log base B. All right, we do, yeah, use base B on both sides. B to the log base B of X gives us our X back. All right, concept review, page 203. All right, create a rational function with vertical asymptote at x equals 10. How about 1 over x minus 10? Right, if you plug a 10 in there, it's undefined. So f of x equals. All right. Remember these, the vertical asymptotes, whenever you get 0 on the bottom. Well, let's come up with another one. How about 2 over x minus 10 times an x plus 5. All right, this one has a vertical asymptote at 10. It also has one at -5. All right, what happens to a graph when it gets closer to a vertical asymptote? All right, so let's say we have a vertical asymptote here. This thing could go up or it could go down. Okay, goes up or down. It gets closer and closer and closer to the vertical asymptote, but it never touches it. All right, in our own words, inverse functions they're functions that undo one another. So like if I had doubling, then its inverse would be taking half of that. Or if I had natural log, the inverse would be e to the x. Or let's see, I had 2 to the x, its inverse would be log base 2 of x. Whenever I put this -1 here, I'm not saying does not mean g, this is not 1 over g, all right, of x. All right, when you put that on a function, it means inverse. I don't think they use that notation in this text, but that's the typical notation. All right. If you put it on anything else, it's an exponent, but for a function, it means inverse. All right. What keywords tell you to use this one? This is continuous compound. All right. For continuous compound interest problems, does P, R, or T have the greatest effect on the final amount? Well, all right, since these are in the exponent, all right, R and T have the greatest effect because they're in the exponential. All right, you can change P by a whole lot, but what matters is most is the rate and the time. So if you have a really high interest rate, you can have a small principal but still make a lot of money. Or if you leave it in there for a long time, even if you have a small amount of principal, you can make a lot of money. All right, because they are in the exponent. Let's find some errors here. All right, part A, if $2,000 is invested at 8.5% compounded monthly for 2 years, then let's see, this amount is invested. This is our rate. Compounded monthly, N is 12 for 2 years. So our amount is P times 1 plus R over N to the NT. So yeah, they have this is right. 1 plus this is wrong, right? R is 0.085. They just put 8.5 in there. But N is 12. And then they have NT. So yeah, they just messed up on the rate there. All right, 129,000 is invested. 3.1% is 0.031. Compounded weekly, N is 52, 6 years. So this is right. That's the principal. That's the rate. This is wrong. 7. No, it's compounded weekly. There's 52 weeks in a year. Then NT. So they got N wrong. N is 52, not 7. All right, $800 is invested. 2.7%. Compounded quarterly, that means N equals 4 times a year. T equals 13 years. So looking at our formula here. All right, there's our principal. That's right, 1 plus, here's our rate over 4. That's right, this is right. And since they're plugging this into the calculator, what they're doing wrong here is this. They need to put this in parentheses. Basically what they did here is this. Right? That's what they did wrong. I mean, it looks right, but without those parentheses, they're doing all of this stuff to the 4th power, and then they're multiplying by 13 instead of raising it to the 13th power. All right, explain the difference between the equations below and how to solve each one. So this first one here, to get the 6x out, we do e to the power of both sides. And we get a 6x equals e to the first power is just e. So x would be e divided by 6. This one over here on the right, we divide both sides by 6. Now we do e to the power of, so we got x is e to the 1/6 power, or the 6th root of e. All right, so totally different. Or we could have done, remember the power rule? And we could rewrite that as natural log of x to the 6th. Remember, if you have an exponent, you can bring it out. It goes the other way as well. If you have a number out here, you can bring it in as an exponent. Then if you did e to the power of both sides, we got x to the 6th. E to the first is just e. So taking the 6th root of both sides. Okay, 2 different ways to solve that one. All right, these two. Let's see, the one on the left, let's add 2 to both sides. Now we take log base 10 to both sides. So x is log base 10 of 7. All right, this guy over here, e to the x, add 2 to both sides. We take natural log. Those undo one another, so x is the natural log of 7, or log base e of 7. All right, those would not be equal. All right, these are not equal. Okay, which of the following equations require a logarithm to solve? Not this one, because the variable is not in the exponent, right? It's right here. We would have P is 50 divided by E to the 8 times 0.45. All right, so no logs. This one, yes, because the T is up there. So B, if we're going to solve that, we can divide both sides by 5. We have a 10 to the 0.03 T. All right, 150 divided by 5 is what? 15? No. 30? Yeah, 30. All right, at this point, we could do really any log we want. We'll do log base 10. Try that again. 10 to 0.03 T. So if those undo one another, we have 0.03 T is log base 10 of 30. So T is log base 10 of 30 divided by 0.03. C, there are no exponents, so we don't need any logs to solve that, right? We would just multiply this thing out. We got 1300. 1300 times 4. times 4 is 5200 R. So 2300 minus 1300 would be 1000. So R would be 1000 over 5200, or 10 over 52. All right, so now we need the formula for the pH. I forget what formula. Let's see. Hydronium ion content formula. So here was our formula. pH equals negative log of H plus. Okay. So that was our formula. So we want to find this. So if we need to inverse this, let's see, we'll multiply both sides by a minus. All right, then to undo the log, I'll do 10 to the power of both sides. So I have H plus is 10 to the negative pH. In this case, it's a 4.5. So let's see here. This is the same as 1 over 10 to the 4.5. Oh, there's a 10 to the x button. Okay. Negative 4.5 equals 10 to the, this is 0.0000316, or 3.16 times 10 to the negative 1, 2, 3, 4, 5 in scientific notation. All right. So Richter scale, I'll have to look this up because I don't remember it either. Richter scale formula. formula here. Oh, no, I can't read that. My Google, you let me down. Just keep bringing up the same crap. Mhm. Wikipedia. Blah, blah, blah. Just give me the damn formula. Anybody remember the formula? It's pretty simple. That's not the one that we used. Richter scale formula. Keeps giving me the same link here. Oh, here we go. R equals log. What is LCLN? LC is the intensity of the earthquake, and LN is the intensity of a standard. That's not the formula we used. All right, I'll try to find the one that we used. All right, we're on page 204. There. There it is. And it's around here somewhere. Richter scale. There it is. It's not what I was finding online, but there's our Richter scale formula. So A. In January 2020, an earthquake south of San Antonio measured 2.9 on the Richter scale. Find its seismographic reading. So we need to solve for X here. So we'll do 10 to the power of both sides. Those undo one another. We have X over 0.001 equals 10 to the R. So X is 10 to the R over 0.001. Here they say R was 2.9. So let's see here. Here's my calculator. 2.9, 10 to the, divide by 0.001, 794,328. In this case, millimeters. All right, for B here, I'm just going to copy this. Repaste it. So for B, what was the seismographic reading for the October Loma Prieta earthquake? And it had a magnitude of 6.9. Well, we can use our same formula right here. So the this is 10 to the 6.9 divided by 0.001. In this case, it's going to be 6.9 10 to the divided by 0.001 7943282 347 millimeters. So that's not millions, that's billions, 7 billion millimeters. That's pretty big. So from A and B, find out how many times stronger the Loma Prieta earthquake was. All right, well, let's take this, divide it by this. And let's see what we get. So that divide by 794,328. And we get exactly 10,000 times stronger. And that's only a difference from a 2.9 to a 6.9. So makes sense. We went up by 4, right? 2.9 to a 6.9, we increased by a factor of 4. Well, guess what? 10,000 is 10 to the 4th power. And there's your connection. All right, now let's see, where were we? We were doing we did this concept review, we did that. That and that. All right, so we're going to do linear equations next time. That'll be fun. So yeah, we'll stop here for now. This is what exam 22. All right. Let's do number 24 here. This is what page? Page 200. There's your number 1. And pick out a second one here. There we go. Let's work on this one. So for this one, we have 2 different banks. And you have to find which one is the better deal. So they don't give you an amount. So what you do is you use how long it takes to double an investment. All right, so that'll be fun. All right, so there's your 2 problems. I will see y'all Wednesday. Oh no, wait. Yeah, we'll do that. All right, y'all have a good day.